Hello, welcome to Ask a Scientist. We have a very special show for you today. We're talking quantum computing with Dr. Diana Prado Lopes Aude Craik. Now, Diana is a Marie Curie Fellow in Physics at MIT and ETH Zurich, where she is studying trapped atomic ions, and we will find out what that means. Now, we first met Diana when she was based at Harvard as part of the Center for Integrated Quantum Materials, and we invited her to the Museum of Science to give a presentation about some work that she had done on quantum computing. And everyone was completely blown away by her ability to really clearly communicate this really complex but fascinating topic. And we just had to invite her back to talk with us some more and to take your questions. Now we'll get to meet Diana in just a moment, but first, my name is Megan. I use she, her pronouns, and I will be your moderator for this session, which means that I'll be fielding all of the awesome questions that you have for Diana. Now, if you're joining us on Zoom, you can start posting those questions whenever you'd like by clicking the Q&A button on your screen, and feel free to add your name and age if you'd like to. I'll try to give you a shout out if we end up answering your question. If you'd like captions, you can click the closed caption button at the bottom of your screen and select show subtitles. Now, if you're joining us on Facebook, please know that unfortunately we cannot see your questions, but we are thrilled that you are tuning in. Now let's get started. I'd like to invite Diana to turn on her microphone and her camera and introduce herself.
Hi, thank you, Megan, for the introduction and for inviting me to participate in Ask a Scientist. Oh, my video hasn't started.
No, here you are. Welcome, Diana.
Can you see me now?
Yes.
Okay. Yeah, thanks for inviting me to participate in Ask a Scientist today. So just to tell you a little bit about what I do, like Megan said, I'm an experimental physicist at MIT, and my work involves trapping one or a few single atoms inside an ultra-high vacuum system, which is basically just a steel chamber that has had all of the air sucked out of it. Now, using lasers and devices called ion traps, like the one you can hopefully see in my background here, we can actually trap a single atom and keep it stopped in one place and look at how it behaves when we excite the transitions between its energy levels. So during my PhD, I worked on using these trapped atoms to make the building blocks of a quantum computer. And now at MIT, I'm working on using them to look for dark matter, which is a mysterious substance that we know makes up something like 85% of the matter in the universe, but we have no idea what it is or where it came from. So one of the things I find most exciting about working in quantum science is that, using just one or a few atoms like that, we can both explore some very deep fundamental questions about the universe around us, like what is dark matter, and make the building blocks for new devices like quantum computers, which have the potential to have very real, practical and exciting applications.
Wow, that is fascinating. Diana, thank you so much for that. You're doing such incredible work, and I thank you for sharing it with us today. Now, today we're going to focus on something you mentioned, quantum computing, and you are so good at explaining this topic. So before we turn this over to the audience, I'd like to ask a couple of questions that I have to kind of get the ball rolling, and I will start with the most obvious. So what is a quantum computer, and what is quantum about it?
Right. So in some ways, a quantum computer it seems very similar to the normal computers that we know. So in a quantum computer, we store information in quantum bits or qubits, which are just analogous to the regular computer bits in a normal non-quantum computer. But a quantum computer actually functions in quite a different way from the standard, or as we call them, classical computers. And that's because it operates in a realm that's governed by quantum mechanical effects. And those effects we normally can't experience directly in our everyday life because the noisy world that we live in kind of washes out these effects, these quantum effects. And that's why whenever we build quantum computers, or we try to build quantum computers, we have to build a system where the quantum bits are very well isolated from the surrounding world. So they're protected from any kind of random interactions with the environment. And to give you an example, the type of quantum computer that I was working with in my PhD, where the quantum bits are trapped atoms or trapped ions, we keep those ions in a vacuum system and suck out all the air out of that steel chamber, exactly because we don't want to have any air molecules or water molecules randomly bumping into our atoms and destroying that quantum. Okay. But so what I haven't told you yet is what these quantum mechanical phenomena are, and that govern a quantum computer, and why they're useful. And the three phenomena that I want to just give you a quick introduction on are superposition, interference, and entanglement. Okay. Now, you may have heard of superposition before. That's the idea that while a normal computer bit can only be in one state at a given time, namely it can either be 0 or 1 at any given time, a quantum bit can be in a superposition of all possible states at once. And this idea seems very powerful because you can imagine that just with 80 qubits, one could represent 2 to the power of 80 states. And if you think about 2 to the power of 80, that number is more than the number of atoms in the observable universe. So it's a very, very large number. And so in other words, if every atom in the universe were a regular computer bit, we still couldn't build a regular computer with enough bits to represent all of those states. Okay, so that sounds really amazing. But however, there is a catch, and it's quite a big catch. Even though you can make a superposition of all of these states with a register of just 80 qubits, right? If you try to read out the state of that register, that superposition collapses into a single state, and all of the information about all of the other states is lost, which, as you can imagine, is not very useful. But this is where the next quantum phenomenon I want to tell you about, called interference, comes in. Now, when you make a quantum superposition, each state in that superposition actually comes tagged with what is called a probability amplitude. Now, these amplitudes are what's known as complex numbers, okay? And a good way to visualize them is to think of them like little arrows that can have different lengths and can point in different directions. Okay? Now, when we measure a superposition, the probability that it will collapse into any given state in that superposition is actually given by the square of the length of that little probability amplitude arrow that's associated with that state. Now, here's the interesting part. By manipulating the probability amplitudes associated with each state using things called quantum gates, which are kind of similar to normal computer gates, like and not, but they're the quantum versions of them, I can make the arrows for a certain set of states point in opposite directions so that their probability amplitudes cancel each other out. This is called destructive interference. Similarly, I can also make the arrows from a set of states line up along the same direction, adding up their probability amplitudes, okay? And this is called constructive interference. Now, when you're designing quantum algorithms, the name of the game is to find ways to manipulate quantum superpositions so that at the end of the computation, we have used interference to cancel out the states that we don't care about, the answers that are wrong, okay? And to reinforce the probability amplitudes of the states that we are looking for, of the right answer, basically. So then when we measure our quantum register, which is in that big superposition at the end of the computation, we know that it will collapse into the correct answer state, if you like, with very high probability. So that's superposition and interference, simply summarized. And finally, I couldn't leave you without telling you about entanglement, which is really at the heart of what a quantum computer is all about. Now, entangled states are states of 2 or more qubits, where the state of one qubit is inextricably linked to the state of another. Okay, so that if you measure the state of one qubit, the state of the other is immediately determined. And the cool thing about entangled states is that they're very compact representations of correlations. So let me give you an example of what that means. If I could have a quantum register, a register of quantum bits, that is in a superposition of all possible input values of some function, some mathematical function, okay? Then I could feed that quantum register into my function and record the output of that function in another quantum register, okay? Now let's call the input to the function x and the output of the function f of x, okay? Now the two quantum registers storing the values of x and f of x are now in an entangled state. That means that if I measure the f of x register, I will collapse its superposition to a single value of f of x, like we're used to. The whole thing will collapse into one. But I will also, because of the entanglement between f of x and x, partially collapse the x quantum register into a superposition, but now only of the values of x that, when input into the function, produce the output value of f of x that I have measured. Okay, so just with these two quantum registers, I actually have a physical representation of the correlations between input and output generated by this function. And the cool thing about this is that I did this without having to measure or record in any way all of the possible values of the function's inputs and outputs, which is what you would have to do normally in a classical computer. So entanglement provides a compact way of storing this correlation information, which is a very, very powerful tool in quantum algorithms. It is also an essential part of quantum simulations of physical systems, because when things like electrons and molecules and atoms interact, their states become very heavily entangled. So those are the three quantum unknowns. That's what makes a quantum computer quantum, to answer your question.
Wow, that is all amazing. So it sounds like quantum computers are very, very different on a very fundamental level compared to computers that we're used to. They're harnessing all these properties of quantum mechanics, so the rules that govern like tiny atoms and subatomic particles, and you're able to, in quantum computing, harness those things like superposition and entanglement, that connection between particles, and do really powerful computations that way. That's pretty incredible. So with all of that power that comes with a quantum computer, what are some of the interesting things that quantum computers could do? Maybe a couple examples, and maybe also what is the most exciting example for you of what we could do with quantum computers? Okay,
I don't know if I have a most exciting example, but I certainly have a class of very exciting things about it. So just to start out telling you, so we unfortunately can't do every calculation faster on a quantum computer. That there are just a very few quantum algorithms that have been discovered so far, which allow us to harness entanglement and interference to do computations faster than normal computers. One of which you might have heard of is called the Shor's algorithm, which can find factors of large prime numbers very quickly and can be used to break certain types of encryption. And so on. But researchers are constantly working on finding out more of such quantum algorithms. But apart from just doing math more quickly, quantum computers are very good at simulating nature. And that's what I find most exciting. So let me explain. Because the building blocks of everything in nature behave in a quantum mechanical way, if you want to exactly and efficiently simulate any process in nature, you need a quantum simulator. You can't actually do it with a non-quantum computer. So quantum computers and simulators will allow us to study nature in a way that we never could before, to simulate and understand things like, for instance, how electrons interact in solids, which may lead us to discover new phases of how to make new phases of matter. We can use them to simulate how complex proteins fold, which should allow us to discover new drugs, new medicines, which is very exciting. And you can even use quantum simulators to test theories about black holes, which is something that you could never dream of doing experiments on Earth, obviously. Wow, that is amazing. So using quantum computers, we could maybe one day be able to just learn more about
nature and how molecules and atoms work, and use that for applications in medicine and a whole bunch of other things. That is really amazing. So this is getting very interesting, and we have a lot of questions rolling in. So I want to get to some of those. So we'll turn it over to there. So let's see. Oh, here we have a really great question from Claire, age 11. What are the biggest discoveries that are made with quantum computing? And I know that quantum computers are still in their very early phases, and we don't have something like a real universal quantum computer yet. So maybe this is sort of along the lines of what you were just talking about. So would discovering more about nature be one of those biggest discoveries? Is there anything else specific that we could do?
Sure, so absolutely. So actually, sort of on the way to making what's called a universal quantum computer. So a universal quantum computer is a quantum computer that works extremely well and is very robust to errors, okay, and that you can encode any problem into and just run it and so on. And it is extremely technically hard to build such a thing, okay. But before we get there, we can build what's called analog quantum simulators. And that's where you take a system that you're interested in nature, say, for instance, a solid that you want to understand how the electrons interact in, okay? And you find an analogous system that you can control in the lab, say a bunch of cold atoms. And you simulate that solid by making those atoms feel an environment exactly like those electrons feel in the solid. And you set up the system, and you sort of watch it evolve. It's kind of like watch nature take its course, okay? And you measure some global property of the system after it evolves. Okay? And just now we are getting to be able to control a number of quantum bits or qubits, such that these analog simulators are going to start pretty soon telling us things about the systems we're trying to simulate, which are new, that we could never compute before. Okay? And that's a very exciting step. We're sort of at the level where we can have 50 of these quantum bits or so on. And around this level, you start to be able to see effects that you would never be able to compute with a classical computer, okay? And so I think some of the most exciting discoveries that are on their way are coming from these analog quantum simulators, where people are understanding more about the physics of how certain systems work by just watching them evolve in the lab, if you like.
Wow, super exciting. So we have some more questions here I want to get to. We have a question. We have a few questions from one of our audience members, and asking you to just expand a little more on how these quantum bits can be in many states at one time, and how that relates to their computing power.
Right. So this is what's called quantum superposition, right? And it's basically a property of these quantum bits that they can. So it's, I guess it's kind of weird to say that they can be in the same state at the same time. It's just that, you know, they are in this state, which is kind of when you measure it, only one state comes out. You can only ever observe them, if you like, see them, and be in one state. But the superposition kind of tells you with what probability it will be in any given state when you measure it. Okay. So this kind of quantumness is very weird, but it's just a property of qubits. And the way it helps you with computation is because, you know, if you want to calculate something and you have a lot of possible inputs to that calculation, you can put your quantum register in a superposition of all of those inputs and just feed that straight in, right? And so that's very helpful. Of course, you always have this problem that whenever you measure, you only get one result out. So you have to figure out a way around this, and that's what I was trying to convey with explaining how this interference works.
Great. All right, let's take some more questions. So we have a question from a viewer about the work that you're doing right now. How are you using quantum mechanics to learn about dark energy or dark matter?
Oh, okay. So this is kind of exciting. So so what we do is actually we look at a transition, and then like a transition between two energy levels in an atom or an ion, which is a charged atom of an element called a terbium. Okay. And there is this theoretical proposal, this idea that there could be a type of particle out there that we haven't discovered yet, we've never seen before, okay, and hasn't been detected. So it could be what makes up dark matter, because it's kind of, it doesn't really interact very readily with anything. So it could be that we've just never detected it before. And this particle, it could make an electron interact with a neutron, okay? This is the proposal. So if this thing were to exist, okay, we might be able to see its effect on energy level differences in an atom. Okay, and let me explain why. So isotopes are atoms of the same type, which are exactly the same, but they have different numbers of neutrons in their nucleus. So if I take two isotopes of the terbium, and measure a transition frequency or an energy level difference in those two isotopes, and I see a tiny difference, that difference could be coming from the existence of this dark matter particle that is making, the isotope that has more neutrons interact with the electrons in the atom in a slightly different way and shift those energy levels. So what we're doing is basically measuring energy level differences in different isotopes of the same element, so just different atoms with the same atom but with different number of neutrons, and trying to see if we see this tiny difference in the energy level differences between these isotopes. And if we spot it, it could be an indication that this particle exists, and this particle could be dark matter.
Wow. So you are just working on like an incredibly tiny scale. So how do you, I have a question that I'm going to throw in. How do you measure that? When you're using these isotopes, these atoms with different numbers of neutrons, and then seeing if there's a difference, and you see some kind of like force that's affecting the energy levels to detect these particles. How do you measure that teeny tiny difference on these teeny tiny particles?
So actually, measuring these energy level differences, what you do is use laser light, basically. So these energy levels are basically the energy levels that the electron can occupy, right? And so what you do is you start out in, say, a ground state of your terbium atom, and then you send in some laser, and this laser will have photons, packets of light, and it will transfer the energy that the electron needs to make the transition from the ground state to an excited state to the electron. The electron will make that transition, and then it will decay back down and emit some light. Now, the electron will only make this transition if you get the frequency or the wavelength of the photon that you send in correct. Okay. Now, the frequency of the photon is a measure of the energy of the photon, and it is also a measure of the difference in energy between that ground state and that excited state of that transition you're trying to measure. So what you can do is you can slowly change the frequency or wavelength of the photons you're sending in, and wait to see at what frequency, what wavelength that transition happens. And when you see that, what the energy difference between those two levels of your atom are. Okay. So you do that for different isotopes, and that way you get a measure of that energy level difference.
Very cool. All right, so let's take one more question, and we have a bunch of questions here taking it back to quantum computing, and we have several people asking for a little more detail on exactly where the power of quantum computers comes from, and you explained that a little in your intro, but maybe is there a really like simplified way to describe like how powerful a quantum computer is compared to a regular computer?
I think so. For me, the thing that is most powerful about the quantum computer is that it naturally encodes these quantum correlations that appear because of entanglement. Okay. And entanglement is something that happens in the quantum realm, but it's something that happens to atoms and molecules and electrons all the time when they're interacting in these systems, these microscopic systems that we don't get to experience firsthand in real life. Okay. And because you can have entanglement in a quantum computer, it's something that you can't efficiently ever simulate on a normal computer. Okay. That makes quantum computers very, very powerful. You are able to, by doing gates in a quantum computer, you are able to make entanglement happen, if you like, at will, because these gates that you do, like in a normal computer, you do AND gates, you do NOT gates, you do NOR gates, whatever. In a quantum computer, you do exactly the same things, but the quantum versions of them. And when you do them, you're actually entangling your qubits together. You're creating this entanglement between all of the qubits in your quantum computer. So it is really the power of quantum computer comes from the ability to use entanglement.
Wow, amazing. So using all these quantum properties gives quantum computers this just like unbelievable power that we can discover more things about nature, possibly design new medicines, materials, all these amazing things. So this is super exciting. Unfortunately, we are starting to run out of time. So Diana, I just want to ask you before we go, is there anything that you want to add about quantum computers or the work that you're doing before we wrap up?
Just to thank everyone for listening and for the really great questions. Yeah, that's all I wanted to say.
Great. All right, well, I have one more question. So some of what you said today may have been pretty exciting and possibly a little inspiring for people who aren't familiar with quantum science or quantum computing. For some of our young audience members who might be interested in getting into this field when they get older, is there any advice that you would have for them?
Well, just to say, definitely come and join us. There are people from a lot of different fields of expertise in working in quantum computing and quantum science, including, physicists, engineers, computer scientists, mathematicians, chemists, material scientists, all sorts of expertise. And are also several different physical implementations of quantum data, and not just trapped atoms, but also superconducting circuits, defects in solids. So all of them have their own technical challenges and advantages. So the opportunities to get involved and to play with different are many and are all exciting.
Wow, that is incredible. Well, thank you so much for all of your questions. This has been an absolutely wonderful conversation. And if you're interested in learning more about Diana's work, you can check out the video of her presentation that she did for the Museum of Science last year called Trapping Atoms for Quantum Computing, where Diana talks about some of that work she did with trapped ions and building qubits for quantum computers. And so that is posted on the Nano Nerds YouTube channel, so you can head over there and check that out. And now we are really running out of time, so I want to thank you, Diana, again so much for joining us and sharing your expertise and your enthusiasm for this field. And now I would like to invite Diana to say goodbye.
Okay, goodbye. And just in case you're interested, here's a link to a blog where we post updates on our research at MIT if you'd like to read about it. Bye.
Awesome. All right, thank you so much, Diana. All right, and thank you so much to all of you for posting your questions. I'm sorry that we did not get to all of them, but there were some really great questions out there. But before we wrap up, I would just like to mention that this week, the Museum of Science participated in Blackout Tuesday, but this is not the end of our engagement. Black Lives Matter as do the invaluable and historically underreported contributions of the Black community to STEM fields, and we will amplify those voices. We have so much good stuff going on over at MOS at Home, so please follow us on social media or check out the website mos.org/MOS at Home to see what we're up to. And if you enjoyed this program, please visit us at www.mos.org/Science Matters to support MOS at Home. That's www.mos.org/Science Matters. Thank you so much to all of you. Thank you again to Diana for joining us. Enjoy the rest of your day, and we'll see you next time.